Welcome back, my geometry students. On our last section, section 1 of chapter 6, I want to do a quick review here. We had learned theorems 6.1, 6.2, 6.3, and 6.4. In theorem 6.1, and the focus, by the way, was entirely on parallelograms. Okay, and today is as well, but we're going to use the reverse of a lot of these, or what we call the converse of a lot of these ideas that we learned. Okay, but previously in our last lesson, theorem 6.1 had stated that in a parallelogram, the opposite sides are congruent. In theorem 6.2, we stated that the opposite angles are congruent in a parallelogram. On theorem 6.3, in a parallelogram, we stated that the consecutive angles, like 1 and 2 in this picture, are going to add up to 180 degrees. Not just that pair, of course, but any pair of consecutive angles. And finally, theorem 6.4 stated that if we were to draw in the diagonals here on a parallelogram, that those diagonals will bisect each other. Okay, they will cut each other in half. So like I said, today, though, is all about doing the opposite of each of these ideas, the converse of these ideas. But not all 4 of these work in reverse. There is not a converse for one of these 4. You're probably trying to guess right now which one you think might be the one that does not work in reverse. Okay, but I will say that the first theorem, theorem 6.1, does work in reverse. Remember, again, theorem 6.1 would state it like this. It would say if it's a parallelogram, then the opposite angles will be congruent. So now we're taking that idea and we're flip-flopping the if and the then. So now we're going to say if it has opposite sides congruent, then it's a parallelogram. So all of these that we're learning today, all these new theorems that we're going to learn today, are all going to end the same way. They're all going to say then it's a parallelogram, because that's what the title of this section, section 2, of chapter 6, is proving that we have a parallelogram, proving quadrilaterals are parallelograms. Okay, now when we use this idea in reverse and say, well, if the opposite sides are congruent, then it's a parallelogram, it's no longer theorem 6.1. Okay, it is now our first new theorem of this section, theorem 6.5. Okay, that's not the only one that works in reverse. Theorem 6.2 works in reverse. Again, we can now say if we know this is true, okay, then it's going to be a parallelogram if the opposite angles are congruent. Okay, and now it's no longer called theorem 6.2. This would be called theorem 6.6. This idea in theorem 6.3 of our previous section is the one that does not work in reverse. Okay, you cannot just say that if consecutive angles add up to 180, that it'll be a parallelogram, because after all, here's our counter example that proves it wrong. What if I were to draw up here a trapezoid in which the top and bottom of this are parallel? So if those are parallel, these two angles, 1 and 2 here, would add up to 180, just like we have over here. After all, there's still a pair of same side interior angles. You know, if I ignore that line there, see it? There's your parallel lines cut by a transversal. So those two would add up to 180. As well as, in this picture, if I were to keep numbering these, 3 and 4 would be another pair. So the two that are on the same leg here and the same leg here of our trapezoid. Okay, those do add up to 180 again. So, and obviously a trapezoid is not a parallelogram. So that's why that idea does not work in reverse. There is no converse of theorem 6.3. Theorem 6.4, though, does work in reverse. We can say now, too, on this one that if we can show that the diagonals cut each other in half or bisect each other, then it's going to be a parallelogram. Now, I do have a replacement for the one that didn't work, though. Oh, by the way, the one where if the diagonals bisect each other, that should be theorem 6-7 on your list of postulates and theorems. And then, like I was starting to say there, I do have a replacement, though, for this one where the angles were supplementary. So I do have still one more way to prove that it's a parallelogram. And this next one, this last one, of course, is going to be then theorem 6-8, following theorem 6-7. And on this one, here's what we need to show for this one. If I want to show something's a parallelogram, if I could show that one pair of opposite sides are both parallel and congruent. So I'm stealing kind of half of this. I'm going to have one pair of opposite sides be congruent. But I'm also going to need to show that that same pair of opposite sides, not a different pair, that same pair of opposite sides are then also parallel. Here, I'll indicate it by just drawing green lines like that. Or maybe arrows like we normally do for parallel. Okay, but it does have to be the same pair, though, of opposite sides that do both. Because if you pick one pair to be congruent and a different pair to be parallel, then I can actually make a shape that's not a parallelogram. Here it is again. What if I made this trapezoid so that this leg matches the length of that leg? But then I had the top and bottom be the two that are parallel. Okay, so there's an example of why it is very important on this theorem that it be the same pair of sides that are both parallel and congruent. Because here I've got this pair congruent and the other pair of opposite sides parallel, and that's not a parallelogram, that's a trapezoid. In fact, this has a special name. Since it has two matching sides, we call it an isosceles trapezoid. Kind of like when a triangle has two matching sides, we call it isosceles. So be careful on that theorem, that new one, 6-8. Okay, all of these technically are new. They're all the converse of the old theorems, except for 6-8. All right, so now let's go ahead and try some problems, because that's really all there is to the notes about the theorems. I'm going to, off to the side of my board here, I know I'm kind of limited on space with this board, but I'm going to try to put a little quick summary again of the four theorems, the four new theorems for this section, off to the side over here. So what I'll do is I'll just make little pictures as a quick handy reference. Okay, so now, again, remember, if I could show the opposite sides match, that would prove it's a parallelogram by our new theorem, theorem 6-5. If we could show the opposite angles match, that proves it's a parallelogram by theorem 6-6. If I could show the diagonals cut each other in half or bisect each other by theorem 6-7, that proves it a parallelogram. And our last, but not least here, our last one that is a whole new idea was the one that we had to show that the one pair of opposite sides, and it doesn't have to be the top and bottom, it could be the left and right, but we have to show that they are parallel and congruent. Okay, so the green's indicating parallel, then the markings, of course, mean congruent, and that is theorem 6-8 that proves it a parallelogram then. In addition to these four, don't forget from our last section, you could always use the definition of a parallelogram to prove it's a parallelogram. Remember, those were the problems where we had to find the slopes of the opposite sides. Okay, but this is four more now additional ways that we can prove that it's a parallelogram. All right, so now let's jump into some problems. And again, we're determining if it's a parallelogram, and I want you to be able to justify why. So in this section, you should be able to use one of our 4 theorems here to prove why. So determine if it's a parallelogram and why. So here's our first one. Let's say I've got some kind of quadrilateral shape here, and this top side has a length of 14. This is 5 over here. That's 14, and that's 5. Okay, so it's a 2-part question, really. We got to determine yes or no whether it's a parallelogram, but we also have to be able to justify why. In fact, on these, you should be able to tell me why or why not. Okay, in this case, you may have noticed by now that our answer here is yes, it is a parallelogram. And I can justify it because I see the 5 matches the 5, the 14 matches the 14. Just like here, I've got opposite sides congruent. So we could say yes by theorem 6.5, or if you'd like to write it out, you could simply say yes because the opposite sides are congruent. Let's try another. Again, we're trying to determine, ooh, that was awful. Let me try that again. We're trying to determine whether or not this is a parallelogram. Let's say on this one that's 20, that's 20, and then these 2 angles are congruent. All right, so on this one, I do have one pair of opposite sides congruent. I see that, 20 and 20. But for theorem 6.5, both pairs of opposite sides have to match. So it's not theorem 6.5. As I look down my list, this one down here, theorem 6.8, does have 2 opposite sides congruent, but I also have to be able to show that those same sides are parallel. Well, if you look at our problem, believe it or not, we can do that. I mean, look, we've got alternate interior angles matching here that create like a Z shape if you follow the angles. See the Z shape? So that's showing if those angles inside of the Z there, if those match, if those alternate interiors are congruent, then the top and bottom have to be parallel and they're congruent. So I can use theorem 6.8 for this one. So this one was a yes by theorem 6.8. Or again, you can explain, if you like, by just saying yes because one pair of opposite sides are both congruent and parallel. All right, let's keep trying these. There's our first 2. Okay, now let's try problem number 3 here. On this one, here's our picture. And I want to know if it is or is not a parallelogram and be able to tell why or why not. If you look carefully at your lengths of the different parts of those diagonals there, you'll see that I do have matching 12s, 12 and 12 here. However, the 7 and the 6 are different. That is not a match there. So they were trying to bait you into using theorem 6.7 to prove it's a parallelogram, but it turns out that they're not a match. So our answer here is going to be no, this one's not a parallelogram. The reason why not, well, because the diagonals don't bisect each other. Because the diagonals don't bisect each other. Okay, or if you think it's easier just to do this, you might say it failed theorem 6-7. Failed theorem 6-7. Okay, so there's another of those problems. Let's keep going with these though. On this next one, let's say that it looks like this, where I tell you this is 42 degrees, 137 degrees, and 42 degrees here. All right, now, something that I failed to mention in my first lesson that of this chapter that I do want you to know is that in any four-sided figure, not just parallelograms, but any quadrilateral, whether it be any of those that I talked about in that lesson the other day, any of these quadrilaterals all have, of course, four sides, but they also have four angles. And all four of those angles, as we've actually learned before, always add up to a certain amount. I don't know if you recall this, but this goes back to chapter 10 that we covered earlier. In a quadrilateral, any quadrilateral, all four angles should always add up to 360 degrees. Okay, so do not just assume that this last angle that's missing is a match for this. Okay, you're going to want to have to do some math here and check things. Okay, if you do the math here, if you take away from 360 these three, so if I take away a 137, a 42, and another 42, I think you're going to find that our missing angle that's left here is not 137. One of the other ways I know that that's the case, because remember, if it was a parallelogram, the consecutive angles, two in a row like this, should add up to 180, and these don't even add up to 180. Okay, if you do your math here, though, you should find that you're left with 139 degrees for that last angle. So again, even though I have a match here and here, I don't have a match there and there. So I cannot use theorem 6-6. So you could say it fails theorem 6-6, or you would say that it's not a parallelogram because opposite angles are not congruent. Okay, they're not a match on a problem like that one. Okay, so if you have a missing angle like that, if you have 3 out of the 4, you could always find the last one, and don't assume that it's just a match. Just because those match does not mean these have to. Okay, do the math. Okay, let's do one more of these at least. Okay, here's our problem. They want to know again, is it a parallelogram? Why or why not? Okay, so on this one, again, be careful. Even though I have matching 6s here, and I have parallel lines on the top and bottom, this is parallel to that. They're wanting you to use theorem 6-8, but it's a trap. Okay, notice on theorem 6-8 again, it has to be the same pair of sides that are both parallel and congruent. That's not the case here. In this one, you can see it's a different pair of sides that are congruent than the pair that was parallel. Because of that, because they're a different pair, I have to say no on this one. Okay, you might say it fails theorem 6-8. or if you're trying to write out an explanation on this one, you might say the same pair of sides were not both parallel and congruent. Okay, it fails theorem 6.8, or the same pair of sides are not both parallel and congruent. And again, I want to emphasize the reason this is going to be a no is it is possible for these conditions to exist and it not be a parallelogram, even though it looks like one in this picture. You know, what if I did this? What if I extended this out a little bit further, and that 6 length right here, what if I ran it like that instead? See that? 6, 6. Okay, these are still parallel. Do you see it makes what we talked about earlier, that isosceles trapezoid? But that's not a parallelogram then. So it could be. I mean, if you swing this inward like that, now it is a parallelogram. Okay, but if you swing it out like that, then it's not. See? So we can't say for certain whether it is or is not. So we have to say no, that it failed theorem 6.8, or the same pair of sides were not both parallel and congruent. All right, so you'll have problems like those. The next type of problem that I want to work with you on are some algebra problems. We're going to have more of those, just like on our last section. And for our first one of these, let's say we had something like this. And here's going to be the one difference too, by the way. On these problems, the wording will be a little bit different. In our last section, they would have said this is a parallelogram, and they would have said find x. Now the wording will be a little bit different, because now, instead of already knowing they're parallelograms, remember this is all about proving they are. So they'll say find x so that it'll be a parallelogram. Instead of saying it's a parallelogram, find x, they'll say find x so that it is a parallelogram. Really, that doesn't change how it's done, though. We're still going to use the idea that if this is going to be a parallelogram, of course, we need those opposite sides to be, you guessed it, congruent, just like theorem 6.5 states. Those opposite sides need to be congruent for it to be a parallelogram. All right, now, you might be thinking, well, that's no different than the problems we did yesterday, Mr. Hess, or in our last section. Well, this one's a little bit different. Did you notice the x squared? So if we set that equal, x squared equals 10x minus 24, it's going to create a quadratic equation. Okay, I wanted to give you a little bit of practice in quadratics again here, and there's going to be one of these on the homework, I believe, as well. Okay, so if you remember right, on a quadratic equation like this, if we want to solve this, one of the first things we do, whether we want to solve it by factoring or the quadratic formula, which I'm sure most of you prefer the quadratic formula, but regardless, no matter what method you use, the first thing to do is get everything over onto one side so that it's set equal to 0 on the other. And I always like my leading coefficient, my leading value, the x squared part, to stay positive. So I'm going to put that on, I'm going to leave it on this side. I'm going to subtract the 10x over. I'm going to subtract the 24, or I should say add the 24 over. I got to do the opposite. Okay, so everything over here is going to be gone. It's going to be set equal to 0. Okay, be careful over here. You cannot actually take x's away from x squareds, or even constants away from x's or x squareds. These all three are unlike terms. Keep them separate and keep them in descending order. So I'm going to put the x squared first, then the minus 10x, and then the plus 24. Okay, and if you remember right, this is the first step to setting it up so that we can start using the quadratic formula, which I'm sure many of you would prefer to use. Remember, the quadratic formula is the minus b plus or minus square root of 4a, or I'm sorry, drew a blank there. You guys are probably singing Stom Song right now. It's supposed to be square root of b squared minus 4ac all over 2 times a. And remember, the a, the b, and the c all come from these coefficients, these numbers in front of each of these. Okay, this will be your a in front of the x squared, which I wrote a 1 there. It's understood to be a 1. Your b would be the negative 10. Don't forget the negative with it. And your c would be this positive 27. So we're going to plug those into the quadratic formula. I can't remember if you were lucky enough to get a quadratic formula from me, program for your calculator. It will do this for you. You could always look it up on YouTube on how to program your calculator to do this too. But it's not too bad. I mean, you just put your numbers in here. So negative b, so instead of a negative 10, which I already have for b, I'm going to put another negative on it. So it's a double negative. See that? Negative 10. Plus or minus square root of the b squared, so negative 10 squared. And you should put that in parentheses. Otherwise, your calculator will only square the 10 and not the negative. Minus 4 times a is 1, c is 24. All over 2 times 1, because a again was 1. Okay, a double negative means it's a positive, so that becomes positive 10. Plus or minus square root of. Now, a negative 10 squared, negative times a negative is positive, and 10 times 10 is 100. Over here, we're going to say minus, and then we're going to multiply all that out. 4 times 1 times 24. So 4 times 1 is 4. 4 times 24 is 96. All over 2 times 1, or 2. All right. Let's do some more simplifying. 100 minus 96 is 4, and the square root of 4 is then just 2. Don't forget over 2 yet. 10 plus 2 is 12. 12 divided by 2 is 6. There's the positive answer. And then there's always a second answer on these. And the second one we get by doing the subtraction below here. So 10 minus 2 is 8. Divided by 2 is 4. Okay, so there's our 2 possible values of x. X is either 6 or 4. You always want to double check and make sure that they're both viable answers, you know. If you were to plug those back into here, make sure you get positive distances for each of these. And sure enough, you're going to see here, if you plug in a 6, you get 60. 60 minus 24 would be 36. And if you square 6, that's 36. The 4, same thing. Square it, you get 16. 4 times 10 is 40. Minus 24 also gives you 16. Okay, so both of those are correct answers. So both of those are possible values of x on that one. Okay, so you're going to have, like I said, a problem on your homework too that, again, has this same concept of quadratic equations involved. So after setting them equal, remember I moved everything over to one side so that it was equal to 0. Once it's equal to 0, now you can start to use the quadratic formula and plug in your a, b, and c and see what you get for your 2 values. And then at the end, always double check both answers to make sure they make sense in the problem. Okay, because occasionally you get, you know, an answer down here that when you plug it in might give you a negative distance, so it's not possible. Okay, but always double check those. All right, so there's a little practice in the algebra problems. Now the last type of problem that I want you to be able to do so that you'll be prepared for your homework here are problems like this where I will be giving you coordinates, and you don't need to draw a picture to get this done, but it's always helpful. I always like a picture. So let's say I've got something like this. We got a point here at -1, 3. Another point at 2, 1. A point at 9, 2. And another at 6, 4. Let's give them some letters too so that we can refer back to them. So they'll call this A, B, C, and D. Okay, now on a problem like this, they're going to ask you to determine if it's a parallelogram. Determine if A, B, C, D is a parallelogram. But here's the catch. They'll say that they want you to determine if it's a parallelogram, and they'll specify which way they want you to prove it even. So they'll say by one of our 4 theorems over here. Actually, not all 4 of these, in fact. One of these we won't be able to use on this problem. There's going to be 3 of them that they may choose from. But one of the possibilities might be, for example, theorem 6.5. So if they specify that they want you to show it's a theorem by this theorem, or that's a parallelogram by this theorem, then we have to show that the opposite sides are congruent. How would you show that on a problem like this? Yeah, you probably guessed it. The distance formula. We're going to have to find some distances in that case. So we'd have to find the lengths of all 4 sides. Okay, this was something that you were probably tempted to do in our lesson, the previous section in that lesson, when we did slopes. But instead we're doing distance. Okay, so we're going to find distances of AD, DC, CB, and BA. If you have your calculator, using the distance program on there would speed things up, of course. Okay, if you don't remember, the distance formula looks like this. It's that big square root where you take x1 minus x2 and you square that, and then add to that y1 minus y2, and it's squared as well. It's essentially the Pythagorean theorem, and whatever you get here is your distance after doing the square root of all that. Okay, so rather than eat up a bunch of time here on the video doing that, I'm just going to kind of reveal some of these distances here. You know, if I had used theorem 6.5, you would have and plugged in your coordinates here for A and D into this distance formula, you would have found that AD's distance should come out to about 7.1. DC's distance, if you plug in those coordinates there into our formula, you would have found that its length is 3.6. CB's distance is the opposite side of this one, so of course we need those to be a match. And what do you know? They are 7.1. And finally, you would find the length of AB by plugging those coordinates into our distance formula. And you probably guessed it, it comes out a match, 3.6. So if I'm trying to prove it's a parallelogram, then by specifically using theorem 6.5, you need to find the distance of all four sides and show the opposite sides match. So of course my answer on this one is going to be yes. Yes it is, because we did have opposite sides that matched. Okay, now I already know the answer is yes, but I want to show you that instead of theorem 6.5, there's other possible theorems here they might ask you to use on a problem like this. So if it had said instead that they wanted you to use, and by the way, they will never use theorem 6.6. 6.6 involves the angles, the opposite angles, and we have no way of showing that these opposite angles match. At least not until I start teaching you some trigonometry, which is a later lesson. So for right now, you wouldn't be able to use theorem 6.6 because we have no way of finding the measure of the angles. Okay, so that's the one they won't use, but they could ask you to do it by theorem 6.7, for example. In theorem 6.7 now, we want to show that the diagonals bisect each other. So you're probably thinking, oh, distance formula again, right? You want to find all these distances. Well, we have a problem there. We don't know, see that point right in the middle here of it? We don't know where that is on this graph. You know, if you were to try to draw in diagonals here and here, you know, you can't just guess where you think they meet there. Okay, but there is still a trick then to do this to show that they bisect each other. Because think about it, that point that we talked about right in the middle is a midpoint of both diagonals. See how it splits that one into 2 equal halves and it splits that one into 2 equal halves? So that point right there has to be the midpoint of both diagonals. So instead of distance, in this case, you'd want to find midpoints. Okay, if you forget how to find a midpoint, remember here's your formula. You take your two x values and you average them. When you find an average, that finds the middle. That's what we're trying to find, is a midpoint. So that would be your new x value. And then you do the same for the y values. You would add them and divide by 2, and that would be your new y value for the midpoint. So we want to find the midpoint of the two diagonals. So we want to find the midpoint of AC and the other diagonal, DB. So we're going to find two midpoints here. All right, so we follow our formula by averaging the x values. So if I'm doing AC, -1 and 9 are my x values. 3 and 2 are the y values, so I'm going to average them as well. Okay, -1 plus 9 is 8. 8 divided by 2 is 4. 3 plus 2 is 5. Half of 5 is 2.5. 2.5. Okay, we do the same for DB. Okay, DB has 6 and 2 for its x values. 4 and 1 for the y values. 6 plus 2 is 8. 8 divided by 2 again is 4. 4 plus 1 is 5. Half of 5 is again 2.5. So no surprise here. We got matching midpoints, and our answer is going to be then a yes. Okay, if your midpoint, if the coordinates of your two midpoints are not exactly the same, then it would be a no. Because we need that point to be shared by both diagonals, and it needs to be the midpoint of both diagonals. Okay, so that's if they ask you to do it by theorem 6.7. That's how we show the diagonals bisect, is by checking the midpoints of the diagonals. Okay, the last possibility, they may ask you to use theorem 6.8. So if the original problem wanted you to prove this is a parallelogram by theorem 6-8, then we need to show, according to theorem 6-8, that one pair of opposite sides are both parallel and congruent. So we won't need these midpoints here anymore. Instead, I pick one pair of opposite sides. I don't care which ones you pick. It could be AD and BC. It could be AB and DC. Okay, it's your choice. You get to pick what pair of opposite sides you would like. I'm going to pick AB and DC. Now, one of the things we had to do was show that they're congruent. I've already done that over here, if you look. We had AB and DC were these two. So I've already shown using distance formula right there that those two matched. Now, you wouldn't need these then. You wouldn't need the AD or the CB. You would just find the distance of those two opposite sides, AB and DC. And then, of course, to show they're parallel, we have to check their slopes. Okay, if you remember right, slope is found by subtracting your y values on top. So y2 minus y1, and x values on bottom. x2 minus x1 on bottom. It's very important you go in the same order on both of these, like left to right, left to right. So when you look at AB, okay, I'm going to go left to right. I'm going to start with the y values, remember? And on top then, 3 minus 1. X values on bottom, in the same order again, left to right, is negative 1 minus 2. If I do the math now, that's 2 over negative 3. And now I need this slope to be exactly the same in order for them to be parallel. So now I go to DC, and on top I subtract my y values. So 4 minus 2. I'm just going left to right. So I'm going to do that again with the x values and say 6 minus 9. 4 minus 2 is 2. 6 minus 9 is negative 3. There you see it. We've got a match. So the slopes are the same. That means the lines are parallel and their distances are the same. So I'm showing that those opposite sides, AB and DC, are both parallel and congruent by theorem 6-8. So no surprise, again, it's yes. Okay? So on those problems, they'll never use theorem 6-6 as a reason or as a way to justify it given coordinates, because I can't find angles. But depending on each of these, depends on what you should be showing me for work. Okay? And please show me your work on these problems. So if I say theorem 6-5, you should have done all the distances of all the sides. Theorem 6-7, remember, was the diagonals, so you wanted to find the midpoint of both diagonals. And then theorem 6-8, I'm going to show one pair of opposite sides, both parallel and congruent, so I find distance and slope of one pair of opposite sides. Okay, you could have just as easily picked the other pair of opposite sides like AD and CB instead. Well, there you have it. That should be enough for you to be able to do your homework for this section. And the homework on this one is pages 301 and 302, problems 15 through 20, problems 22, 23, and 26 through 32. Okay, if you have any issues, don't hesitate to contact me. Again, you can text me on Remind and say you need some help. Maybe send me an email. We can find a way then to get in contact and help each other here if you need some help. Alrighty, good luck.